Okay, welcome everybody to the last section from chapter 6. And in this section, we'll learn about convolutions and how they apply to Laplace transforms. Okay, so the last thing that we're going to do in this section is talk about convolutions. So section 6.6 is convolutions. Okay. Now there are different kinds of convolutions, but for us, a convolution h of t is going to be the function, well, the convolution of f and g. So when you convolve two functions, you get a function. And so if I take f and g and convolve them, for us, that's going to mean you take the integral from 0 to t of f of t minus tau times g of tau d tau. Okay. All right. So that is the convolution of f and g, and it is a function. Okay. Now, suppose we look at, there we go. Okay. Now, notice that by a simple change of variables, f convolved with g at t could also be written as the integral from 0 to t of f of tau g of t minus tau d tau. I'll let you check that. That's a very simple calculus 1 change of variables. Okay, and so this convolution has some properties. Some are easy to check. 2 of them are easy to check. 1 of them is hard to check. 3 of them are easy to check. 1 is hard to check. One is that if you take the convolution of f with g, it's the same thing as the convolution of g with f. That's basically this observation above. Okay. 2, if you take f convolved with g, that gives you a function. You could convolve that with a third function. Okay, so that would give you the same thing as taking f and then convolving it with g, convolved with h. In other words, convolution is associative. And by the way, this says convolution is commutative. Okay, so it's commutative, it's associative. Another property of it is that it's distributive. If you take f and convolve it with g1 plus g2, that is f convolved with g1 plus f convolved with g2. So convolution is distributive over addition. Okay, convolution is distributive over addition. Okay, and then finally, this one's easy to see. If you take f and you convolve it with 0, that's the same as 0 convolved with f, which is 0. Okay, so if you convolve something with 0, you get the 0 function. Okay, and this is really easy because if you take f and you convolve it with g1 plus g2, the integral of the sum is the sum of the integrals. So that's obvious. This one is the tricky one to work out just because the change of variables gets messy. And this is basically this easy change of variables observation we made up top. Okay, so these are properties are pretty obvious, but you must be careful because, for example, convolution is not multiplication. Multiplication. Okay. because, for example, if you take f and you convolve it with 1, you do not get f in general. Okay. For example, no room on the sheet. For example, suppose I take sine of t and convolve it with 1. So that's the integral from 0 to t by the definition of convolution. Remember the definition of convolution. Whoops, definition of convolution. You take the first function and you evaluate it at t minus tau. The second function and you evaluate it at tau, but that function is just 1. And then you integrate with respect to tau. Okay, so now let's compute that. Let's go ahead. So I make a change of variables. I let u be t minus tau. Then du is d is minus d tau. Okay, and so and if tau equals 0, that says u is equal to t. And if tau equals t, that says u is equal to 0. So sine t convolved with 1 is equal to the integral from t to 0 of sine of u with a minus du, because d tau is minus du. Okay, so if you integrate sine, you get back minus cosine. So this, and there's a minus sign out in front. So this becomes cosine of u evaluated from 0 to t. So that's cosine of 0, which is 1, minus cosine of t, okay, which is definitely not equal to sine t. Okay, so sine t convolved with 1 is definitely not equal to sine t. So it's not at all like multiplication, even though that asterisk might make you believe that it's close to it. Okay. Okay. So why do we even bother to mention convolution? We mention convolution because it has a very nice property with respect to Laplace transforms. Suppose that f of s is a Laplace transform of little f of t, and capital G of s is a Laplace transform of little g of t. Then the Laplace transform of f convolved with g at t, so the Laplace transform of the convolution, is the product of the Laplace transforms. And remember, for every statement about Laplace transforms, you get one about the inverse Laplace transform. So the inverse Laplace transform of the product of two Laplace transforms is the convolution of the inverses they came from. Okay. Now the proof is a bit messy. Maybe I will do that in a future lecture, but this, or in one of our question classes. But it's basically one where you have to very carefully interchange the limits of integration. I want to get on to some examples and not make this lecture too overly long. So that would take an extra 15 minutes or so to go through the proof. So I think I'll pass on that right now so we can do some examples. So for example, suppose you are asked to, here's h of s. It is a over s squared plus a squared. Find the L inverse of h, which we'll call little h of t. Okay. Okay. All right. So here's how I would do this now that we know this trick. So h of s, I'm going to write as 1 over s squared times a over s squared plus a squared. So I think of the first one as f of s, and the second one is g of s. So here's my capital F, and here's my capital G. So the inverse Laplace transform of capital F, in other words, the inverse Laplace transform of 1 over s squared, if you look in your chart, that is exactly t. And the inverse Laplace transform of g of s, the inverse Laplace transform of a over s squared plus a squared is sine at. Okay. So by the theorem, the inverse Laplace transform of capital H is, here's my little f, this is my little g. So it's the convolution of f convolved with g. So in other words, that's the convolution of s with sine t with sine at. So that is the integral from 0 to t of t minus tau sine a tau d tau. Oops, left that off there. Okay, so how do you integrate that? You have to work that out. Okay, so one part of that, there's two integrals there. So that is, the first integral is t sine a tau d tau. So that one's easy. And then you have minus the integral from 0 to t of tau sine a tau d tau. And that one is an integration by parts. So when you integrate the first one, this is simple enough. You integrate sine, you get back minus cosine. So there'll be a minus and a cosine a tau evaluated from t to 0. Okay. And here you have to do the integration by parts. So you let u be tau, then du is d tau, and dv is sine a tau d tau. So v is minus cosine a tau divided by a. Whoops, I left off my divided by a here. Sorry. Okay. Okay, so when we do the integration by parts and there's a minus sign out in front of it, it's u times v. So we got to be careful with that minus sign. So that'll be a plus tau cosine a tau over a evaluated from t to 0. And then you have a minus and a minus. So that'll be a plus the integral of v du. Okay, so v du has another minus in it. So this will be minus 1 over a integral from 0 to t cosine a tau d tau. Okay. All right, so let's evaluate these things where we have it. So this is a minus t cosine a t over a. And then you subtract the value at 0, so that'll be a plus t over a. Okay. And now we evaluate this at t. So we'll get a t cosine a t over a, and then subtract the value at 0. When I subtract the value at 0, I get 0 because of this one. And then notice this, this term cancels this term. Okay. And now we have a minus 1 over a, but you have to integrate cosine. When you integrate cosine, you get sine a tau divided by a, but there was a 1 over a out in front already, so it's an a squared, and now you evaluate that from t to 0. So this becomes t over a. And now when we evaluate at t, I get minus 1 over a squared sine a t minus the value at 0, but that's 0. Okay. 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 So you could leave it like that. You could make it a 1 fraction, however you like. That's the inverse Laplace transform. Okay. Let's do one more example. one more example. Okay, so suppose I look at the equation y double prime. Um, let me so water. Okay, plus 3y prime plus 2y equals cosine um, alpha t rather. Y of 0 is 1, y prime of 0 is 0. Okay. Okay, so take the Laplace transform on both sides of the equation. Okay, when we do that, what do we get? We'll get an s squared y minus s y of 0 minus y prime of 0 plus 3sy minus 3sy of 0 plus 2y is equal to the Laplace transform of cosine alpha t, which will be s over s squared plus alpha squared. Okay. All right, so let's see. The y prime term is 0. This is y of 0 is 1. So those two terms will go to the other side. We'll pull out the s, the capital Y. We'll have an s squared from this one. This goes to the other side as an s. This is a 3s times a y. This is a minus 3s times 1. So on this side, it'll be 3s. So that becomes 4s, obviously. And then here we have a plus 2. And then we already had over there an s over an s squared plus alpha squared. Okay. Okay. I'm sorry. This should not have had an s with it, looking back on this. Here we took the Laplace transform of y prime. So it's sy minus y of 0, period. No s. Okay. No s. Okay, that was just sloppy on my part. Okay, so y of s is equal to s over s squared plus 3s plus 2 plus s over s squared plus alpha squared times s squared plus 3s plus 2. Okay. Okay. Now, notice when we look at, shoot, golly, copied that wrong. S plus 3. There we go. Now that's right. Okay. Okay. Now you notice that the denominator factors. Okay. So we have two pieces here. Let's do each piece individually. So let me call this one, I don't know, I want to save F and G for over here. Let me call this one H of S. Okay. So if I look at H of S, what do I have? I want to figure out what the inverse Laplace transform of that guy is. So that's S plus 3 over the denominator factors to S plus 1 times S plus 2. Okay. So I could think of that as S plus 2 plus 1 over S plus 1 times S plus 2. Okay, so by my handy dandy algebra bag, that's S plus 2 over S plus 1 times S plus 2 plus 1 over S plus 1 times S plus 2. Okay, so these two cancel. And now if you invert 1 over S plus 1 using your Laplace transform tables, you will get e to the minus t. Okay. And now this one. You think of this one as the product of the inverse Laplace transform of 1 over s plus 1 times, I'm sorry, you take the inverse Laplace transform of the product of 1 over s plus 1 times 1 over s plus 2. Well, let's see, this one, when you invert it, gives you e to the minus t. This one, when you invert it, gives you e to the minus 2t. And the theorem about inverse Laplace transforms says that the inverse Laplace transform of a product is the convolution of the things it came from. So this will be e to the minus t plus e to the minus t convolved with e to the minus 2t. Okay. All right. So that's this one. That's this first piece. Okay. Now, what about the second piece? Now we have to look at that piece. So now to invert, we want to take L inverse of the second one there. I'm going to think of that as s times s squared plus alpha squared times 1 over s plus 1 times s plus 2, which is the second term in this denominator up here. Okay, so this is the second term. I break it into two pieces. I take this one by itself times that piece. That's what I wrote down here, except I factor that denominator. Okay. All right, so I think of this one as f of s and this one as g of s. Okay, so now notice g of s is exactly what we inverted here. And we found that the inverse transform of that one is the convolution. Okay, so what is this one going to be? This one is going to be, you taking the inverse Laplace transform of a product. This one, when you look up on the chart, if you invert that, you get cosine alpha t. And you take the convolution of that with the inverse Laplace transform of this guy. And the inverse Laplace transform of this guy is the convolution of e to the minus t with e to the minus 2t. Okay. Okay. All right. So that's you can do that in any way you want. You could leave it like this. I'll be happy if you leave it like this on the test. There'll be one place on a test where I'll ask you to write out the convolution and work it out. It's not so hard to do. For example, if we wanted to do the convolution of e to the minus t with e to the minus 2t, this is just the integral from 0 to t of e to the minus t minus tau times e to the minus 2 tau d tau. So that's the integral from 0 to t of e to the minus t, e to the plus tau, e to the minus, so that's an e to the plus tau and then e to the minus 2 tau. So that will be an e to the minus tau d tau. The e to the t is not the variable of integration, so that comes out in front. When you integrate e to the minus tau, you get minus e to the minus tau. I'm missing room for a minus sign, so I get minus e to the minus tau. And you evaluate from t to 0. And at t, that's a minus e to the minus t, e to the minus t, so that's an e to the minus 2t. And then when you subtract the value at 0, so this is a minus e to the minus 2t. You subtract the value at 0, that'll give you a plus e to the minus t. Okay, so it's e to the minus t minus e to the minus 2t. Okay. And then you could take the convolution of that with the cosine. That's pretty messy because now you have to do the integral of a cosine times an exponential, and that's integration by parts twice. So that's really messy. Okay. Okay, so I hope you enjoyed this section and that the examples were clear on the convolution and how to use it in ODEs using Laplace transform methods. And I will see you soon in class. Bye.